Welcome to the Explainer. You use AI tools every day, but have you ever stopped to wonder what's really going on under the hood? Well, in the next few minutes, we're going to break down 20 of the core concepts that power pretty much everything you see in AI today. So let's start with the big one. How does an AI go from just a bunch of letters on a screen to actually understanding what we mean? It's a really fascinating process, and it all starts with breaking our language down into pieces a computer can actually work with. All right, this first group of concepts, you can think of them as the absolute foundation. They explain how a machine learns to read, interpret, and, most importantly, find the meaning in our words. Okay, so at the very heart of all modern AI is the large language model, or what everyone calls an LLM. At its core, it's just an incredibly powerful prediction engine. I mean, if you give it a phrase like, all that glitters is not, its one and only job, based on everything it's ever read, is to predict the most likely next word, gold. That's it. But here's the thing, an LLM can't just read whole words like you and I do. First, it has to use a process called tokenization. This breaks our sentences down into smaller, meaningful chunks called tokens. So a word like eating might get split into two tokens, the root word eat and the suffix ing. This helps the model really get a handle on the underlying grammar. So now we have these tokens. Each one gets converted into a long string of numbers called a vector. Now, the best way to think about this vector is as a set of coordinates that places that token on this giant, multidimensional map of meaning. And on this map, words that mean similar things like king and queen or dog and puppy are placed really close together. But, words can be tricky. The word apple here has 3 totally different meanings depending on the sentence. So how does the AI figure it out? Well, that's where a mechanism called attention comes in. It's a clever way for the model to look at the words around apple, like tasty or revenue, to figure out the correct context. And that attention mechanism, it's the absolute key ingredient inside the transformer architecture. You can think of the transformer as the powerful engine design that runs basically all modern LLMs. It works by stacking many, many layers of this attention mechanism, which lets the model understand not just simple context, but also super complex stuff like sarcasm or metaphors. Okay, so we've got the building blocks for understanding language. Now let's talk about how these models actually learn from all that data and, get smarter. A massive, massive breakthrough in this area was self-supervised learning. See, instead of humans needing to label every single piece of data, the model basically teaches itself. It'll grab a sentence from the internet, hide a word, and then just try to guess what that word is. Do that billions and billions of times, and it starts to internalize the patterns of human language all on its own. Now, once a model has all that general knowledge, you can specialize it through a process called fine-tuning. This is where you take that general jack-of-all-trades model and train it just a little bit more, but on a very specific, high-quality dataset. So for example, you could fine-tune it on a whole library of medical textbooks to create a specialized AI assistant for doctors. But how do we make sure a model is actually helpful and safe and not just a weird text prediction machine? Well, that's where reinforcement learning from human feedback, or RLHF, comes in. This is a stage where real people review the AI's answers and rate them. Good answers get a thumbs up, bad answers get a thumbs down. This is the crucial step that teaches the AI what we actually want and helps align it with human values. To get even better results on really complex problems, we can use a cool technique called chain of thought prompting. Basically, instead of just asking for the final answer, you tell the model to show its work, to break down its reasoning step by step. And what's amazing is this dramatically increases the chances of it getting the right answer. So, when you combine all of these training methods, you go way beyond simple text prediction. You start to create what are known as reasoning models. These are AIs that can actually analyze a problem, strategize, and work through it in a logical way. Okay, so a model is trained. But here's the problem. The world keeps changing, right? How can we get it to use information that's brand new, or even interact with other apps? This next part is all about connecting AI to the live, real world. A really important technique for this is called Retrieval Augmented Generation, or RAG. This slide lays it out perfectly. First, before it answers your question, the AI retrieves relevant, up-to-date info from a database. Then it augments your original question with all this new information. And finally, it generates an answer based on that much richer, more current context. Now, this is all supported by a few key tools. There's few-shot prompting, which is basically giving the AI a couple good examples right in your prompt to steer it in the right direction. Then you have vector databases. Remember that map of meaning? These are special databases built to search that map incredibly fast to find the right info for RAG. And finally, there's the Model Context Protocol, or MCP, which is a new standard for letting AIs talk to other apps and tools securely. Now, when you put it all together, a model that can reason and the ability to use tools and access live data, you get AI agents. These are a really big deal. They're not just chatbots, they're autonomous systems that can actually work on complex, multi-step goals for you, like planning an entire trip, from doing the research all the way to booking the flights. And this entire practice of designing and managing this flow of information, the prompts, the documents you retrieve, the tools you give it access to, that whole discipline has a name. It's called context engineering. Okay, finally, let's look ahead. Where is all this tech going? Well, the next big frontier is all about making models both way more capable and, at the same time, much, much more efficient. The future is absolutely multimodal. For a long time, AI was pretty much just about text, but that's changing fast. Now models are learning to process and understand different modes of information at the same time. A multimodal AI can look at a photo, listen to the audio from a video, and read the caption to get a much richer, more human-like understanding of what's going on. At the same time, we're seeing this really interesting split. While the giant LLMs are amazing general-purpose tools, we're also seeing the rise of small language models, or SLMs. As you can see here, they're smaller, they're trained on more focused data, and they're designed to be hyper-efficient experts in just one thing, often at a tiny fraction of the cost. But look, whether a model is huge or tiny, efficiency is everything. Making them smaller and faster so they can run on your phone or laptop is a massive priority. And one of the most powerful ways to do that is with a technique called quantization. The best way to think about it is like compressing a really high-resolution photo. You lose a tiny, tiny bit of detail that you'll probably never notice, but the file size gets way smaller. Quantization does pretty much the same thing to an AI model. It reduces the precision of the numbers inside it, say from a super detailed 32-bit number down to a simpler 8-bit one. That one change can shrink a model's size by up to 75%, making it way faster and cheaper to run. And that's it. A quick tour of 20 concepts that are shaping the future of AI. We're building systems that can reason, that can see, and that can connect to our world. And that leaves us with one final big question. What happens next when these systems start to learn, adapt, and improve, all on their own?